In this video, we will study Thevenin's theorem. Thevenin's theorem states that a complex linear circuit can be represented by a voltage source in series with a resistor. So if we have, for example, a linear circuit, and we have, let's say, these two terminals, A and B, and this is our linear circuit. Now this circuit can be quite complex. It can have many sources, many resistors, independent, dependent sources. But we can represent it with a very simple circuit, which is just a voltage source and a resistor in series. So these are the two terminals, A and B. The resistor in series is called Thevenin resistor, or RTH, and the voltage source is called VTH. So any linear circuit can be represented by a single voltage source and a resistor. The advantage of doing so is that in many cases, we have a load. For example, here, we have a load which can vary, which can have different resistor values, for example. And every time we change the load, we need to solve the entire circuit. If we do not draw the Thevenin equivalent, then we will have to place the load over here, and we will have to solve this complex circuit many, many times, which can be quite tedious. So therefore, it is much simpler to find the equivalent circuit. So this representation is the Thevenin equivalent. So this is the Thevenin equivalent circuit. Now this theorem can be applied only to linear circuits. Fortunately, the resistive circuits that we are studying so far, they are all linear. And by linear, we mean that if the input to our system is multiplied by a constant, the output increases by the same amount. And also, if two different inputs are applied to our system, the output can be obtained by applying a single input at a time and then adding the response of the two inputs. For now, we will assume that our circuit is linear and we want to represent it with a Thevenin equivalent model. These two circuits are going to be equivalent if they show, or if they demonstrate, the same voltage current behavior at the output. And for us, the output are these terminals, A and B, where we are supposed to connect the load resistor. For example, if the linear circuit on the left produces a certain voltage and current, the same voltage and current is obtained using the equivalent circuit. Then we can say that these two circuits are equivalent. So let's consider first that if we keep the output terminal open circuit. So if we keep it at open circuit, so we will solve our linear circuit between the two terminals A and B, keeping the terminals open circuited, and we will find the voltage at these 2 points, VAB. All right, so now if this is the voltage that the circuit produces when it is open circuited, if we now consider our Thevenin circuit, and if we keep this open as well, because we want to ensure that the two circuits are equivalent. So if the output terminals are open circuited, then the voltage at the output in this case will be VTH. So now comparing the two circuits, left and right, we can say that the Thevenin voltage is actually the open circuit voltage. Here, OC stands for open circuit. So this tells us how to find the Thevenin voltage. The way we find the Thevenin voltage is that we open circuit the terminal A and B. So we do not connect any load resistor between those two terminals. And then we find the voltage at those terminals, and that is our Thevenin voltage. So this actually does solve part of the problem, which is to find the Thevenin voltage. The second task is to find the Thevenin resistance, RTH. To find RTH, we will turn off all the independent sources. We will first consider a circuit example in which we only have independent sources. So we will see how to find the RTH for that type of circuit. Later on, we will consider a circuit where we have dependent sources, and we will explain how to find the Thevenin resistance of a circuit that includes dependent sources. For now, let's consider the circuits with only independent sources. So to find the Thevenin resistance, we will turn off all the independent sources. By turning off, we mean a voltage source. For example, if I have a voltage source between 2 points, a voltage source will be replaced by a short circuit. So the voltage source was supposed to be here, and this voltage source was, let's say, producing a certain amount of voltage. So to turn this voltage source, what we will do is that this voltage source will now produce 0 volt, and 0 volt means a short circuit. So you see the voltage difference between these 2 points is 0 volt. So that's how we turn off a voltage source. For a current source, if, for example, I have a current source like this, and I have a certain amount of current that is flowing in the upward direction or downward direction. So to turn off this source, we will replace it with an open circuit. So this would look like this situation. And the reason why we are doing this, because the original source was producing a certain amount of current, and now to turn off the source, we want to ensure 0 current. And 0 current will only happen if we open the circuits like this. So therefore, this is called turning off the sources. So a voltage source will be replaced by a short circuit, and a current source will be replaced by an open circuit. Once we do that, then we will see that this is our circuit, and we have turned off all the voltage sources. So let's call this one a dead linear circuit. And these are the 2 terminals. And we will see from this point what is the resistance of the circuit. The resistance of the circuit will be our Thevenin resistance. So this way we can find the Thevenin voltage and the Thevenin resistance, both of them. Once we calculate both of these values, then we will construct our Thevenin equivalent circuit, which will be represented like this. We will have VTH and RTH. These are the 2 terminals, A and B. So this will represent a very complex circuit in a very simple way. Then we can connect different loads to this, and we do not need to resolve the entire complex circuit again and again. We just need to solve a very simple voltage divider. So let's see an example to explain this method. So we have an independent voltage source and an independent current source. The current source is producing a current of 2 ampere, which is flowing upward. And we have a 10 volt voltage source. Let's say this resistor is 2 ohms, 4 ohms, and then we have 10 ohms over here and 6 ohms. And these are my 2 terminals, A and B. And this resistor is 6 ohm. Now this circuit is not too complicated. However, this will just serve to show how to apply the method. Now the terminals A and B are the points where our load resistor will be connected later on. The first thing is that I want to find the Thevenin voltage. So the first step is find VTH. So to find VTH, we know that the Thevenin voltage is the open circuit voltage of our circuit. So the terminals A and B are open right now. So all we need to do is to find the voltage from here to here. That is our open circuit voltage. Now you see the terminals A and B are open. So this will have some significance when we try to solve this circuit. I will solve this circuit using nodal analysis. So for nodal analysis, I will assume a reference node. So this is my reference node where the voltage is 0 volts. And I can see that in my circuit, I have 2 different nodes. Let's say this is V1 and this is V2. So these are the 2 nodes in my circuit. To apply nodal analysis, we will consider node 1 and node 2, and we will apply KCL to both of these nodes. To apply KCLs to the nodes, we need to assume the directions of currents. So let's say this is the current which is flowing into the node. This 2 ampere is also flowing into the node. And I will assume that there is a current over here which is leaving the node. Similarly, the current over here is entering V2. And the current over here is leaving V2. And the current in the 6 ohm resistor must be 0 because it is an open circuit. The output is open circuit, so the current in the 6 ohm resistor is 0. So there is no current flow in that resistor. Now let's focus on node 1. At node 1, according to KCL, the current that is entering the node should be equal to the current that is exiting the node. Current in must be equal to current out. The current in to the node V1. Now remember, we have 0 volts over here. So we see on the bottom wire, we have 0 volts. Therefore, the voltage over here must be 10 volts. So I have 10 volts over here. And on the other side, I have V1, and the resistor is 2 ohm. So this current in this branch, which is entering V1, should be equal to 10 minus V1 divided by 2. So this is the current that is entering the node 1. Similarly, a 2 ampere from here is entering the node. So 2 amperes are entering from here. So these are the two currents that are entering node 1. The current that is leaving node 1 is V1 minus V2 divided by 4. All right. So we got that. Now let's multiply by 4 on both sides. This will give me 20 minus 2V1 plus 8 equals to V1 minus V2. Now I can write negative 3V1 plus 28 equals negative V2, or I can write negative 3V1 plus V2 plus 28 is equal to 0. Finally, if I want to change the signs, I can multiply by minus 1. So this will give me 3V1 minus V2 equals 28. So this is my first equation. So we got our first equation by applying KCL at node 1. Now let's check. Now let's apply KCL at node 2. So at node 2, the currents that are entering is this one. This is the current that is entering the node, and the current that is leaving is V2 divided by 10. So the current that is entering is V1 minus V2 divided by 4. So I have I in equals to I out. I in is V1 minus V2 divided by 4, and I out is V2 divided by 10, I believe. It's V2 divided by 10 because V2 minus 0 is just V2. So V2 divided by 10. Now I can write it as 10V1 minus 10V2 equals 4V2. And from here, I have 10V1 minus 14V2 equals 0. Or I can say that V1 is equal to 14 divided by 10V2. And 14 divided by 10 is 1.4. So V1 equals 1.4V2. So this is my second equation. And this equation tells me the value of V1 in terms of V2. And now I can put this value of V1 in equation 1. So let's say we put in equation 1. So if we do that, my equation 1 is 3V1. So I will have 3 times 1.4V2. And then we have negative V2 equals 28. Negative V2 equals 28. That will give me 4.2. V2 minus V2 equals 28. Or we have 3.2 V2 equals 28, which means V2 is 28 divided by 3.2, or V2 is equal to 8.75. So this is the voltage at node 2. Now let's see node 2. The voltage at node 2, we just calculated that to be 8.75. Now, if the voltage at V2 is 8.75, and if the current in the resistor R6 is 0 ampere, so the voltage drop across this resistor will be 0 volt according to Ohm's law. So therefore, the voltage at this point at V2 will be the same as the voltage at this point. So therefore, our open circuit voltage is the same as V2. So we can say that VTH, which is the open circuit voltage, so VTH is equal to V2, which is 8.75 volts. So we got the first step, that we have calculated the Thevenin's voltage. Now the next step is to find the Thevenin resistance. Find RTH. To find the RTH, we need to turn off all the supplies. So let me copy this circuit. So we need to turn off the independent sources. This 10 volt is an independent voltage source, and this 2 ampere is the independent current source. So we need to turn off both of them. To turn off a voltage source, we will replace it by a short circuit, because we want to get rid of this 10 volts, and the 10 volts should become 0 volts. To turn off the 2 ampere current source, we will replace it with an open circuit, because we want 2 ampere to become 0 ampere. So that's the turning off the two sources. So therefore, the circuit will look like this, that we will have a short circuit over here, then the 2 ohm resistor, then this 2 ampere will be replaced by an open circuit, so that path is not there. And then I will just draw with a dashed line, just to remind us that there was a current source previously, which is not there anymore. And we have the resistor, then we have this 10 ohm resistor, and then this 6 ohm resistor. And then finally, we have our two terminals, A and B. This is 2 ohms, and this is 4 ohms. So this is our representation of the circuit after turning off the voltage and the current sources. And this circuit, we will call it the dead circuit. Now looking between these two, looking from here, between the terminals A and B, this is our input resistance of this circuit. And the input resistance of the circuit, of the dead circuit, is actually the Thevenin resistance. So all we need to do is to just solve the circuit, find the value of the resistance. First of all, I see that 2 and 4 ohms are in series, so I can replace them with a simple 1 resistor, and that will be 2 plus 4 is 6, and this is 10, and this is 6. The next step is that we see that 6 and 10 ohm resistor, they are in parallel, right? So these two are in parallel. So therefore, the parallel combination of 6 and 10 is 6 times 10 divided by 6 plus 10, which is 16. So that is 60 divided by 16, and that is equal to 3.75. So the parallel combination will be now represented by one resistor and then the 6 ohm resistor. So this is the parallel combination, which is 3.75, and here we have 6. So now this is our circuit, and these two are in series. So therefore, the total resistance of both of them combined is the sum of the two. So 6 plus 3.75 is simply 9.75. Now you see, this is our input resistance, which is the same as our Thevenin resistance. So our Thevenin resistance is 9.75 ohms. So we have calculated both the Thevenin voltage and the Thevenin resistance. So our final equivalent circuit is something like this. These are the terminals A and B. Our Thevenin resistance is 9.75 ohms, and the Thevenin voltage was calculated earlier to be 8.75 volt. So this is our equivalent circuit that can replace the original circuit, which was slightly more complicated than this equivalent circuit. Now, to show that these two circuits will behave the same, they will produce the same amount of voltage and the same current in any resistor that is connected between the points A and B. They both will produce the same response. So we want to show that. So for that, we will now consider any value of the load resistor. We can assume any value, and we will then solve both circuits to see if we really get the same values for voltage and currents. So now let's test these two circuits. And let us assume that the load resistor is 1 ohm. Okay. All right, so this is our original circuit, and I have connected a load resistor of 1 ohm as shown over here. And with this load resistor connected, I want to see the load voltage VL and the load current IL. So I want to calculate these two values, And then we will find the same for the Thevenin equivalent circuit and see if they are the same in both cases. So to solve this circuit again, I will assume, so we will do nodal analysis. This will be our node 1, this is our node 2. At node 1, I will apply KCL, and the current entering must be equal to the current leaving. So therefore, I have 10 minus V1 divided by 2, plus 2 ampere is also entering. This should be equal to the current that is leaving, and that is equal to V1 minus V2 divided by 4. And we previously solved this equation, and after rearranging, we will arrive at this equation that 3V1 minus V2 equals 28, or I can say that V1 is 28 plus V2 divided by 3. So this is the first equation. To get the second equation, I will apply KCL to node 2. And the current, so let's apply over here the KCL to node 2. The current that is entering node 2 is V1 minus V2 divided by 4. And the current that are leaving node 2 are V2 divided by 10, because this is V2 minus 0 divided by 10, plus V2 minus 0 divided by 7. And it is 7 because in this branch we have 6 plus 1, 7 ohm resistance connected, because 6 and 1, they are in series, so therefore the series is the summation of the two, which is 7. All right, so we got this finally. Now I can say that maybe I will write it this way: V1 divided by 4 is equal to V2 divided by 4 plus V2 divided by 10 plus V2 divided by 7. And V1 we previously calculated was 28 plus V2 divided by 3. So V1, so I can write V1 as, so from here, I'll find the value of V1 and put it over here. So I will have 1 over 4, 28 plus V2 divided by, divided by 3. And this is equal to V2 times 1 over 4 plus 1 over 10 plus 1 over 7. I took the V2 as a common factor out. And after solving and rearranging, we can now get 28 divided by 12 is equal to V2, 1 over 4 plus 1 over 10 plus 1 over 7. And this from the left-hand side, if I take this to the right, this will become negative 1 over 12. And now we can find V2 from here. Solving all these terms in the parentheses will give me 0.4095, 0.4095 V2 equals to 28 divided by 12, which is 2.33. Therefore, V2 is equal to 5.7 volt. So we found V2 to be 5.7 volt. And now let's go back to the circuit. I have 5.7 volt here, 5.7 volt approximately. And I want to find VL. All right, so now you can see that this is a simple voltage divider. I have 5.7 volt and I have two resistors. This 5.7 volt will be divided between these two resistors depending on their values. The larger resistor will drop most of this voltage, and the smaller resistor will be dropping a small portion of this voltage. So let's apply the voltage divider rule. And in this case, our source voltage is 5.7. So therefore, we can say that the load voltage is 5.7 times the resistance, 1 ohm, where we want to find the voltage drop, divided by the resistance of the total resistance, which is the series combination of both of them, and that is 7 ohms. So we will have 5.7 divided by 7, which is 0.814. So this will be our load voltage. So the voltage across the load resistor will be 0.814. So we found the load voltage. Also, the load current, according to Ohm's law, the load current will be the load voltage divided by the load resistance, which is 0.814 volts divided by 1 ohm, and therefore the load current is 0.814 ampere. So we found the load current as well. These are the values that we obtained from the original circuit. And now you can appreciate, you see, if I change the load resistance from 1 to 2 ohms now, I have to redo all these calculations. And this is a very time-consuming matter. So every time I change my load resistance, I have to redo all these calculations. The Thevenin equivalence circuit gives us a way to avoid these extra calculations, in which we solve our circuit once, and then we have a very simple equivalent, and every time we change our load resistor, we do not have to do all these calculations. But first, I want to show that the Thevenin equivalent circuit will actually give me the same load voltage and the same load current as we have obtained from our original circuit. So let's reconstruct our Thevenin equivalent circuit with a 1 ohm load connected. So you see these were our terminals, and I have a 1 ohm load connected. My Thevenin resistance was 9.75 ohms. So this was 9.75 ohms, and the voltage, Thevenin voltage, was 8.75. So these are my Thevenin voltage source and the Thevenin resistance. And now we have connected a load of 1 ohm. Again, I want to find the load voltage, VL, the voltage drop across 1 ohm resistor. And again, this is a simple voltage divider rule. So this 8.75 will be dropped partially across this resistor and this resistor. So to find the load voltage, VL, we can use the VDR, which is 8.75 now, multiplied by the resistance or the resistance value across which I want to find the voltage, divided by the series combination, which is the total resistance. And now it is 9.75 plus 1, so that's 10.75. So we have 8.75 divided by 10.75, and that is equal to 0.814. 0.814 volts. This is the load voltage. And because the load resistance is 1 ohm, so therefore the load current will be this load voltage divided by 1 ohm, which will remain the same. So it will be 0.814 ampere. So now let's compare these values, 0.814. And you can see 0.814, 0.814, and you can see here. So the two circuits actually produce the same voltage and the same current in a load resistor, which is 1 ohm. And if you want to investigate this further, you can use a different value of load resistor, and you will see that both circuits will produce the same amount of voltage and current. So therefore, the two circuits are equivalent. And now you can recognize the strength of this method is that any load resistance, we can replace any load resistance, and we can find the load voltage and the current very quickly, very easily, and without doing all these extra calculations. So that's the advantage of Thevenin's theorem. So this was Thevenin's theorem with independent sources. I hope you enjoyed this video. Please consider subscribing. I'll see you next time. Bye for now.